There are familiar faces. Hi, Robert. Breakfast is served. Yeah, I don't know if we can lower the lights a little bit, just so that the rays will look a bit more visible. Sorry, coffee is yeah, so I'm just going to myself. It's working? Yeah. It's starting. It's like protocol to do that, right? Starting in -1 minute. That's probably what it is.
See, you brought the bag of money, $20 bills. Otherwise, this exam doesn't go forward.
Well, to bribe you guys, there's coffee and tea in the back, as well as cookies. So please have yourselves. Not enough? Alright. So I don't know who's joining us from remote, but I hope you can hear me. And if you can't hear me, now will be a good time to text, because I'll not be able to answer it later on. Anybody? Just invites, immediate, available, probably. Unfortunately not.
All right, so what's the century research? I was clicking. When did you know? Probably. Oh, okay. Yeah. Nate, so Andrew, just for your benefit, what we did, Robert and I didn't involve ourselves into preparing this because we already submitted this before.
Yes.
So, but the way we run things is we ask you to prepare a talk which should be 45, 50 minutes, not longer.
15
We can
minutes.
interrupt with questions. The audience can ask questions at any point, and then we're going to let the audience ask more, and then the audience will leave, and it'll just be the committee and CS field members if anyone else wanders up. Okay. So with that, we'll get started.
All right, good morning. So my name is Zeke, and for today's talk, I'm going to present to you data networks that you want to use, with special focus on performance, reliability, security, and usability. So here are some of the pet peeves in today's network. Right? They are slow, they're unreliable, insecure, and it's hard for users to operate and maintain.
What is a network?
Computer data network.
Like you say, who, where, slow, what? Is this a network I'm using in this building, or what is this a network?
It's in general any kind of data network that you use. So it's based on internet technology. Right? So in the first part of my talk, I will describe, I'll talk a little bit about why networks are slow, unreliable, and insecure, and how we've actually overcome some of these problems. And in the later part of my talk, I will describe some measures in which we can take to improve the operability and the understandability of these networks. So first of all, how do we get ourselves into this terrible state? Okay, I would say there are 2 points. The first one is Ethernet, and the second point is spanning tree protocol. Now, first of all, how prevalent is Ethernet, and why is Ethernet important? So Ethernet accounts for more than 85% of all data networking technologies as of October 2013. The real number is probably a lot higher than that. Now, what about spanning tree protocol? Okay, and what is spanning tree protocol, and why should I care about it? Now, the sole purpose of spanning tree protocol is to prevent loops in the network. So in a network topology like this, there are no loops, and this is a valid network topology. On the other hand, if you added one extra link, such as to create one loop, this is not allowed. Not allowed by spanning tree protocol. And this dates back to a standard that was established back in the 1990s. So here's a more complicated example. Perhaps you have a network that has a topology like this. Then what might happen in a spanning tree run is that the spanning tree protocol might disable some of these links. By disable, I mean they turn off the link activity, and the net effect is to leave behind a spanning tree that could look like this. Right? There are no loops in the network. Some of these links are strategically turned off, but the end effect is to produce a tree across the network.
Can I ask another question?
Go ahead.
When I go from here to Europe, does Ethernet all the way?
No, it's not Ethernet all the way.
So the middle block here is something else.
It could be something else. It could be FTDI. I don't know what technology carries the undersea cables, but it usually is not Ethernet.
So do you
For
think
long haul kinds of.
for fairness to Andy, you might want to circumscribe the kind of network you're specifically interested in,
Okay.
rather than appear to be redesigning the whole internet.
Okay, sure. So this talk targets Ethernet networks. Ethernet networks are, like they should be pretty familiar with. You've seen all these wall jacks. You plug the cable into
babies
get
that?
it into your computer. So that kind of technology is called Ethernet, and Ethernet, by its own nature, is meant to be plug and play, meaning that it should be very easy to use. Like you plug one end of the cable into the wall, the other end into your computer, and you should have connectivity. Likewise, if you wanted to extend the network, it should be as simple as taking one network switch, plugging a cable from that to a different network switch, and now you've extended and reached the network segment. So this is how Ethernet works in a nutshell.
It doesn't, like in this building, where does Ethernet start and where does it stop? It starts right here, and it stops where?
There's no real start or end point. I mean, I would say every connection point where you plug the device in is an end point, right? And it's sort of like the start of the network. There's no end in the network. I mean, it's just one huge.
So the
web
thing we're
of
doing that's starting to
connections.
confuse me is that I understand your work as being a software-defined networking architecture aimed at enterprise networks. One entity owns the network. It's this building, it's the university campus, but somebody owns it, controls it, as opposed to standards. It does not, in fact, branch into IBM where we have no visibility, and then out on the far side.
That's correct.
But why did we say any of these things?
So
You're making it hard for Andy to follow the specific scope.
okay, so I apologize for that. So I had this impression that the talk would be a little bit technical. So I'm sorry if you do not fully comprehend the technology. I also unfortunately do not have the time to go through all of the basics in Ethernet networking. I'm sorry.
I think we're not confused about what Ethernet is. We're confused about your assumptions about the scope of it.
Okay, so the scope of the work. Sure, sure.
But here's Andy asking, Cornell to France, actually in his case, Finland, and you're answering as if that's part of the scope of your work.
No, I didn't say that. I was
Well, you certainly answered as if that was.
This will only be Ethernet networks for data centers. So a privately owned Ethernet network would be the scope of this work.
But for example, you have two ends here,
Okay.
and it makes it look like things are going end to end. So in this building, I think mostly when I send an email to someone else in this building, it goes up very high place and back again. It doesn't go end to end. So it goes out of the Ethernet and back in again. It looks like your network goes end to end on the
It
inside.
may or may not, depending on where your email server is located. So typically, a server would be located outside the building. So that's a possibility.
But also think about that we have some software that going on for the base class. But anyway, the Exchange server that Cornell CS uses is we have it to the other 100, but we wanted to test. It is in the building. Your email server to the Cornell, your client to the Cornell server would actually go out.
In this special case, yes. In the general scenario, not always.
Yeah.
Right. So I really have to move on because we're going to run out of time.
Actually, you have to answer questions if somebody else.
Okay. So what are some of the implications of a spanning tree? All right. First of all, a spanning tree links are potential bottlenecks because a lot of flows will share some of the links, and therefore some of these links could be overloaded. Secondly, there's always only a single source of destination path. It's the network property of a tree. Third of all, there are long recovery times on tree breakages. This is one of the side effects of the spanning tree protocol. It takes a little bit of time to regenerate the links and rebuild the tree. And lastly, data travels over critical paths. Again, this is something to do with the single source of destination path and the terminal state of the network.
So I'm a little confused about how you're assuming spanning tree is used. So the spanning tree is a protocol that constructs an overlay tree on top of the hypergrade.
Exactly.
Then there's a separate question of what protocols put data on the hypergrade. There's nothing to stop them from using it.
Exactly. And this will be addressed in the later slides. Right. So let's look at the first 2 points. I mean, to address your question, we're assuming that for a typical kind of application that doesn't try to do anything special on the spanning tree, then these are the same kinds of constraints that we'll face. Now, the first 2 points affects performance. The second and third point affects reliability, and the second and fourth point affects security. So if you look at all of these problems in composite, you realize that the one big problem with Ethernet networks is that there's only a single source of destination path, and this seems to be the root of all the problems. So intuitively, the answer is okay. If that's the problem, then maybe multi-path forwarding is the answer. But what exactly does multi-path forwarding really mean? All right. First of all, in any kind of multi-path standards, you cannot actually violate what STP gives to you. With some special exceptions, we'll talk about that in a little bit. Right. However, you can employ some tricks to give the illusion of multiple paths and forwarding. Now, what I mean by that, I'll cover that in the following slides. So here's a sampling of some of the multi-path technologies that are available today. It's not by any means a comprehensive list, but to motivate our solution, I will first describe 2 modern approaches to multi-pathing, and then you decide whether it's really multi-pathing or not. Now, in the first case, let's study how the smart path assignment in networks actually works. So they call it SPAN in short. And what SPAN actually does is that it provisions multiple VLANs. In each VLAN, you have a different spanning tree. Right? And the idea is that if I encounter a failure, then I will switch over to a VLAN that will circumvent this failure. Right? So these trees are pre-computed. For example, VLAN 100 in Spain will correspond to this spanning tree. And then in VLAN 101, also in Spain, this would correspond to the other spanning tree. Now, one key thing to note is that there's only one VLAN assigned per flow, meaning that for any single flow, it will only traverse across one single spanning tree. All right? However, in aggregate, if you have many flows and you randomly chose each flow to map to a different VLAN tree, then what will happen is that you will spread the load out. Right? So in aggregate, it's multipath in that way, you could say so. But if you look a little bit at the scaling literature, right, I'll point out one part that I believe deserves closer scrutiny. And it says over here that, in effect, Spain doesn't really know when a network has failed. Right? It relies on little symptoms and signs to know that a network has failed. And then, based on that, it reacts by switching you over to a different VLAN tree. Okay, and the problem doesn't end over here. Right? In order to use Spain, you need special drivers, you need to modify the DHCP server, and you block out the use of certain VLANs. So this seems like a very inconvenient solution. Also, this solution fixes the problem only after it occurs, meaning that after you discover that there's an outage, then you do the repair. Right? And in this time, you notice that there's a little bit of data disruption, during which you cannot do any communications at all. So how about something else, like MPTCP, right? That's a very mature kind of technology, approved by the Internet Engineering Task Force in 2013. And what does MPTCP actually say? If you look at the design document, right? And I was zooming on one little part of the document. The document says, if I have multiple addresses at a host, then I can assume that I'll have multiple paths in the network, right? And the question I have for you is, are these assumptions actually valid? So consider what MPTCP would do if it was running on an Ethernet network, okay? Now, suppose you are the sender on the left. The two red circles corresponds to both your network interface cards, so your multi-phone on this side. Your recipient is on the right side of the network. There are two red circles indicating both the network interface cards for the recipient. Right? What actually happens when you send two subflows to the network? Okay, so the first flow will take a path like this, right? And then the second flow will take a path like this. Now, what you actually see over here, there is still the sharing of some of these links, right? And also, you have the problem that when a subflow fails, there is still a time lag in discovering the failure, and then there's even more time required to shunt the load onto the remaining subflow. So again, we're repairing the problem, we're fixing the problem only after we've discovered it. Right? It's kind of a reactive solution. So now that we've seen two multipath examples, you should really be asking yourself, is this really multipath? Right? Are our existing multipath approaches flawed? So first of all, I assert that there's too much guesswork for topology. Things like MPTCP saying, if I have multiple addresses, I can assume disjoint paths in the network. I can assume multiple paths in the network. Doesn't seem like a very good assumption to me. Secondly, pre-computed solutions for failures. So in solutions like Spain and related kind of work, you find that if you pre-provision for these failures in that way, and then you say, once I get a failure, I will switch to some pre-computed solution. The danger in this approach is that your resulting path may not be optimal, right? There's also extensive reliance on each of these solutions on hardware and software support. So for example, you need multi-homing, you need multiple network interface cards, right? Or else you need special drivers, you need DHCP servers to be more powerful. So this seems like a very clumsy kind of solution. And most importantly, all of these solutions fix the problem after the fact. Only after it's happened, then you fix the problem. And this always results in disruption.
Sorry for using so basic. Outside of this building, in this Europe problem, there is also multiple nodes. And my understanding is that is a multiple factor. Things are fishing around and going all kinds of ways. Is that correct? And which of these solutions is that?
You're right. So if you talk about the internet on a general scale, then in terms of the reachability graph, there are multiple ways to get from one location to another location. However, when you send a flow, so when you're actually doing some communication, say you connect to google.com, right? And google.com.sg, for example, the Singapore server, what is likely to happen is that your data will flow over one single path from the US to Singapore. This will be deterministic. It's governed by some other protocols that will be outside of the scope of our discussion. So they're not. So you're right. Yes, there are multiple paths, but you only use one path in this communication. So let's move on. So let's take a step back and ask ourselves, how should we do multipath correctly? Okay? It must always begin with the understanding of the network topology. So I say that the questions about networks, the question about the underlying topology of the network, is best answered by the network itself. Yes.
The classic way to think about reliability is that
be able to make it more reliable because the entire stack with your. Okay, so what's the point now? Okay, so resilience is one of the properties that we provide, and you're absolutely right that in the end-to-end kind of argument, you could say that you could just pass it back on to the application and let them deal with the reliability. In some situations, this may not be acceptable. So, for example, if I'm running a telesurgery kind of session, right? So telesurgery means I'm a doctor or a surgeon operates remotely and has a TCP connection to a remote site that has the actual robotics and the cutting knives and so on. Now, in this kind of situations, can you really just say that I'll pass the buck on to the application and let the TCP protocol deal with the retransmissions and so on? Well, the answer is yes, you probably could do that. But that seems to be dangerous to me because if you ever have any kind of a hiccup and the application doesn't deal with it in a timely way, then you could result in lives to be lost, in short. So there are some cases where even though the protocol provides for the reliability, you may nonetheless want a better guarantee than what it provides. And this is essentially what I was talking about for economic purposes. Does that answer your question? Okay. All right. So where were we? All right. So I said that the questions about network should be answered by the network itself. And these answers should be dynamic, it should be intelligent, it should not be pre-computed. All these answers should reflect the current instantaneous reality of the network itself. And furthermore, most importantly, they should definitely not be by any kind of guesswork. So no more saying things like, if I have multiple addresses, then I have multiple paths in the network. Okay? And here's our approach. We make no topology kind of guesswork at all. We make very, very sure to understand and to deduce the correct network topology before we answer questions about what paths are available. And these paths are calculated dynamically, meaning that as and when the paths are required, they're computed. Right? And in one of the most important departures of existing approaches, we make sure we use all of the disjoint paths simultaneously. Right? This is no longer one of those one path and over the average number of paths you get multiple paths in use. Right? Also, we proactively provision to prevent failure, and we do not require any kind of special software hardware on the client end, meaning that if you have a device that works on the network today, it will work on our network. So this system is not wishful thinking, all right? It exists today. It's called IronStack, and it's running part of Gates right now. So how do we do this? First of all, we use a technology called OpenFlow, and in the next few slides, I'll define what these terminology are. Right? So we will then figure out the network topology and employ some clever means to prevent loops while at the same time evading the restrictions that spanning tree protocol gives to us. Next, we will do some very selective packet processing using network processing units, and then we will use the disjoint paths that are available to us all at the same time. If we do things right, we can also make the network appear like a regular one. So again, you do not have to make any kind of modifications to the hardware in order to use this network. Right? So let me just take a step back and describe what OpenFlow is. OpenFlow is traditionally defined as the separation of the control plane from the data plane in controlling a network switch. But I think it's easier for me to define it as a way to decouple the decisions about data movement from the actual data movement itself. So there are two entities involved, right? One of them is called the OpenFlow controller, and this is a software entity that calls the shots. Right? The hardware, which is the OpenFlow switch itself, is the device that accelerates the flows based on the decisions that the OpenFlow controller makes. Okay, now what about network processing units? So network processing units are in general just packet processors. They can take many different forms. But the form that we decided to use in our research is the NetFPGA version. The exact hardware we use is called the Xilinx NetFPGA 10G cards. And what these network processing units do is that they provide a special function on each of the ports. Right? So for example, one port could do packet deduplication, one could do parity packet generation, one could do encryption and so on. The nice property is that they're daisy chainable, meaning that the output of one of these ports could be sent as the input to another NPU's port. And now we have two actions done back to back. Furthermore, it's very easy to scale capacity. So in a situation where you need more packet processing than your NPUs can handle, all you have to do is get more NPUs and attach them to the same switch. So a high-level idea, a high-level architecture of a system operated by IronStack would be as follows. You have some arbitrary topology, possibly multiple disjoint paths as well, and then you have NPUs attached at strategic locations in the network. So for the purposes of this animation, which will show to you how data transmission works across an IronStack network, we will assume that the left side will be the transmitting side and the right side will be the receiving side. So I call this the ingress switch because this is the first point where data enters a switch. And that will be the egress switch because that's the point where the data will exit the switch and enter the client. So if A is trying to transmit to B, conceptually this is what would happen, right? A piece of data gets sent up to the switch forwards it up to the NPU processes the packet, and sends it along disjoint paths. Right? Now, then they get forwarded on to the egress switch. The egress switch forwards it up to the NPU. The NPU does some processing on the data to regenerate the original piece of data. Right? This is then forwarded down to the client, to the recipient. Okay? So from the point of view of A, the network performs exactly as is expected. Right? It doesn't know anything about disjoint paths, nor does it have to know anything about disjoint paths. Right? And similarly, recipient B receives the data as expected. There's no out of order kind of stuff. And it receives a network just as it should be, what you can explain to. Go ahead. Exactly. So that's a very good question, and you will soon. So this will be covered very, very, very soon. Okay, I promise you. All right. So let's see. First of all, what does disjoint paths actually buy us? Right? We can borrow. Let's borrow an idea from this array system. Right? You may have heard of this technology called a redundant array of independent disks. So this is a set of schemes that provide performance and reliability on disk devices. Now, if we apply the same kind of technology, the same kind of treatment to disjoint paths, we treat each disjoint path in the network as though it's an independent disk in a RAID system, then what you can actually do is you could attain performance and reliability improvements similar to the RAID system. And I call this the redundant array of independent links, or RAID. So now let's talk about how you do things like improve the performance. Improving the performance in a disk system is similar to RAID 0. So in RAID 0, you will send disjoint sets of packets down each path. And then what you will do is you will label the packets on the ingress switch by rewriting the MAC destination addresses. Then on egress, you make sure you reorder the packets and restore the MAC destination address. I will show a picture of how this works in the next slide. But I just thought I wanted to address something right away. And the disadvantage of this approach is, of course, that we have very high latency. Right? So your question was, what happens if the network paths fail and so on? Yes, in the case of RAID 0 or Rail 0, this will severely impact the algorithm. So you're absolutely right about that. But the upside to it is that if you can tolerate the latency, then what will happen is that you can get the next node bisection bandwidth available to use all the disjoint paths. Right? The disadvantage, of course, is you get high latency because now you have to wait for packets coming from the storage. So here's how it could look like. Suppose I have 3 packets coming out from the sender, and I would like to deliver it to the receiver. So I would send 1 packet on each of these individual disjoint paths, which then get reordered before delivery of the egress switch. So now the receiver will receive all the packets and in the right order. Now, how do we improve reliability then? So again, we can borrow an idea from the redundant array.
So there's no calculation here, but you're assuming that the molecular nodes at the end are enough capacity to necessarily do
Yes, that's correct. That's correct.
That's not part of the calculation.
It's not part of the calculation. Okay, so how do we improve reliability? Again, we can borrow.
How much memory is in that FPGA card now?
How much memory? I think it's 270 megabytes of DRAM and 27 megabytes of SRAM.
And these are running at 10 gig?
These are running at 1 gigabit per second for evaluation purposes.
So you really don't have much time. I mean,
You're right.
So this comment about latency, it had better not be a lot slower because you would 100% never be able to do it.
Exactly. So you're right that buffering space will be an issue, especially if you're trying to run this at high speed at the same time, and we're trying to do things like looking out for duplicates and reordering packets.
So why not flip it around and just say you're going to assume identical latency to within a few microseconds, but you'll gain on bandwidth.
We could do that. We just wanted to make the solution as general as possible.
Yeah,
So
but
we
that
don't
statement
make
invites the next question, and then the answer is not satisfactory. So we end up at a dead end. Whereas if you just said we assume that there's, that the latencies are essentially synchronous, then you could respond to me that I actually have time for, I don't know, 72 microseconds delay. Worst case, I assume is 12. So I've got time, and then they would be perfectly happy instead of saying dead end or finding another dead.
we don't make any,
saying, but I think it's true.
we don't make any assumptions on the differences in the latency, and we assume that there will be enough buffering in the packet processor, the NPUs.
So that's the assumption about latency.
Yeah, but there are lots of solutions to tackle the lack of buffering space, right? You don't buffer free packets, for example. You could hash the packets and match on the hash instead. Hash could be like 64 bytes, and now you can store a lot of packets in 27 megabytes as well. So this will provide enough buffering for quite a few hundreds of milliseconds, and I think that should be more than enough. If you exceed that bound, then yes, our NPU will not be capable of reordering the packets. So there is a service limitation on this technology. Yeah, absolutely. Okay, so let's move on. Now, in improving reliability, the disadvantage is that you waste bandwidth on making the redundant copies. Right? If you're making one extra copy, one similar copy of the packet for every disjoint path, and you're wasting n-1 copies of them. I mean, n-1, you're wasting the bandwidth of n-1 of the paths, right? Especially if there are no losses at all. So, how would Rail 1 actually look like? Rail 1 could be something like this. You would send one packet, which is replicated on each of the individual switches, and then on the replicate of each of the disjoint paths, and then on the egress switch, you will remove the duplicates before you deliver the packets, right? And so now I described, the Rail 0 and Rail 1 system. The question you should be asking is, I have Rail 0 on one hand, which gives me the maximum bandwidth for the worst possible latency, and then I have Rail 1, which gives me the best possible latency but the worst possible bandwidth. Right? Is there some kind of a middle ground? Right? And the answer is yes. If we apply a technique like RAID 4, okay, to our system, then essentially what happens is that for n number of paths, we could compute one parity packet out of the n-1 packets. Right? And again, if you send this down the individual disjoint paths and reorder and assemble the packets as usual, then you could get improved network performance and improved reliability without sacrificing on extremes of latency and performance as well. So the disadvantage is that there's a high computational cost, and this you will see later on when I describe the results. So how would that actually work? So in a real class system, I could have like 2 packets, right? I have 3 disjoint paths and I send 2 packets, n-1. Now on one of the disjoint paths, I will compute a parity packet. The parity packet is simply the XOR of the contents between the packet that I sent on the first disjoint path and the second disjoint path. Now on the egress switch, I only need 2 of the packets to reconstruct the original packet itself. Okay, and all I have to do is regenerate the original packet, reorder, remove any duplicates, and then deliver it out to the receiver. So RAID 4, Rail 4 provisions for up to 1 failure. What if you want to tolerate an arbitrary number of failures? Right? You could tolerate up to 2 failures with a system like RAID 6 or Rail 6. And this will actually involve a very complicated parity computation. Now, to simplify this, you can use some kind of a combination of like RAID 1 plus 0. And essentially what will happen is you can take a packet, replicate it k+1 number of times, and then you send each of these individual packets down a disjoint path. All right? And with this, you're able to tolerate up to k failures. It's not going to be the most efficient representation in terms of bandwidth, and it's not going to get to the best latency, but this is a very cheap way of solving the problem. So for expediency reasons, I will not show the picture illustrating how a system like that would work. But let's go on to the results. So this is the experimental topology that we used for our ICDCF paper. And in this topology, we have a host A that belongs to send data to host B. The bold lines in this graph represent the spanning tree links. And quite critically, you should pay attention to the fact that everywhere else in the spanning tree, or everywhere else in the network, has a bandwidth of 10 gigabits per second, but only the 3 links going out from the ingress switch to the middle 3 switches have a link capacity of 1 gigabit per second. Okay, so this will become the limiting factor in the spanning tree. So intuitively, right, this is our micro benchmark results, and I'll go over it right away. Intuitively, what we would actually expect, and we should, okay, so hold on. Let's try to compare these results with what we think is attainable by vanilla Ethernet. Okay, so in vanilla Ethernet, if you run it on spanning tree, then we expect that the bandwidth would be capped at 1 gigabit per second, right? And in fact, if you look at our micro benchmark results, we find that this is exactly what happens. So in the Ethernet spanning tree, the bandwidth is 0.85 gigabits per second. It's not exactly 1 gigabit per second because we're not able to configure a switch, and the maximum packet length was set to 536 bytes. So the ratio of the header to the payload was very large. So 0.85 was in fact the saturating bandwidth of the on the spanning tree network. Now, if we use rate 0 or real 0, what actually attained is a perfect 3.0x improvement in bandwidth, right? Meaning that we are now saturating all 3 possible paths in the network as well. Now, in real 4, we attain a 1.5x improvement. We would expect a 2.0x improvement, but as I mentioned earlier, there are some computational overheads. Right? It's not exactly straightforward to compute the parity and reassemble things again. So because of this latency that we incur, the bandwidth drops to about 1.5x. Nonetheless, it's an improvement over vanilla Ethernet. Okay, now on the latency side of things, real 0, 1, and 4 are completely unaffected by transmitting on the disjoint path. Right? So there's no improvement, but there's no drop in performance here. And these numbers that you see, although they seem to be about 10 milliseconds, 0.01 milliseconds slower, about 100 microseconds, they are really an artifact of scheduling, first of all. So there's a lot of noise when you get down to a position like that. And second of all, there is some latency incurred in the FPGA processing. So this is sort of to be expected. But within a very good degree, you can say that the latencies are not affected. Okay.
That 1.5 improvement also came at a cost of 1.5 burden on the network.
That's
So it came at the cost
not
of
exactly a 1.5 burden on it.
Wasn't it 3 to
3 to 2. Not exactly 1.5.
Right.
Okay.
But that's not your concern, or?
It is a concern, you're right. So there is a bandwidth efficiency improvement when you use real 4 as compared to, say, using real 1. But the improvement is not going to be exact improvements.
It's also exactly a burden on the network of the same factor of improvement.
Yes, compared to Ethernet, that is correct. That is correct. But remember, we're trying to maximize performance over here. We don't really care so much about the utilization. Now, in the case when we inject cross traffic, so notice that in the diagram, notice in the network topology, I have something that says cross traffic generator on the egress and the egress switch. So these cross traffic generators actually run iCurve, and what they do is they try to have saturating traffic going through the Ethernet spanning tree. Okay, now if we compare our setup, okay, to the regular Ethernet spanning tree, then on real 0 we obtain a substantial improvement because a lot of data can now be transferred on the non-saturating, the unused disjoint paths, and we use whatever we can get from the saturating. Okay. Now in real 1, there's a substantial improvement as well because all the packets simply just avoid the saturating path. And in fact, looking at the factor of improvement is not really accurate. If you look at the transfer bandwidth, this is 0.85 gigabits per second, which is exactly what you expect if the data was moved solely by the non-saturating, the unused disjoint paths. And real 4 again offers an improvement somewhere between real 1 and real 0. Now on the latency side of things, real 1 and real 4 are clearly unaffected because you will just use the disjoint, the extra paths to get the packets in a timely manner to the recipient. And on average, real 0 has improved latencies because for most of the time, you're transmitting on the non-saturating or the unused links, and part of the time, you'll be using the saturated link. So on average, you'll see an improvement in the latencies as well. So another question you should be asking is, how will some of these techniques that I described earlier fare on the same setup, right? And we talk about MPTCP, for example. How would MPTCP perform in something like this? Now, MPTCP, because it's bound by the same spanning tree setup, should perform exactly the same as Ethernet. Unfortunately, we did not get to benchmark this. However, this is one area that we could do for the follow-up paper. Now, as for Spain itself, Spain might not be a very fair measurement, but you can clearly see that Spain will not be able to use all of the disjoint class at the same time. Remember, they net one VLAN to one subfloor, meaning that the maximum kind of bandwidth they can get will be 1 gigabit per second. Right? All right, so I finished talking about the performance and reliability part of the talk, and now I'd like to switch gears and talk a little bit about security. So RAID doesn't handle security, all right? However, the nice thing is that we can reuse our existing NPU structure and disjoint path infrastructure to provide improved confidentiality and anonymity. Okay? So what is confidentiality and anonymity? Confidentiality just means if I send data across a network, no one should be able to see what the contents are, all right? And anonymity just says that if I send, if I want to talk to person A, then nobody on the network should be able to know who I'm talking to. Okay. Now, to handle security, we borrow some ideas from a paper called information slicing. Right? And in the confidentiality technique, what we actually do is we take a plain text and we select some number of paths we want to use, a threshold number of paths, then we do some fancy matrix multiplications, matrix transformations, and then we generate the individual slices. So this is a lot easier if I show a diagram. Right? So here's an example. I have a plain text M, right? And now I say I want to use up to 4 paths, and I want a minimum threshold of 3 paths, meaning that I need at least 3 fragments in order to reconstruct the original plain text. I can tolerate up to 1 loss in that way. Okay, so what I'll do is I'll first partition the matrix, divide it out such that I have a V by M matrix, V being the minimum number of fragments I have, and then M is just the result of the division. All right, and then I'll generate a full rank random matrix A with D prime by D, and I will multiply these two together. All right, the result will be a transform matrix. This will contain some unintelligible data, and now the information slices can be obtained when you concatenate this transform matrix with the random matrix. So slice 0 will correspond to row 0, slice 1, slice 2, and slice 3. And you send each of these individual slices down the available discount pairs. Now on the recipient side, what would you do to recover the original data? Now again, you only need 3 out of the 4 fragments. Any 3 out of 4 fragments will be fine. Right? Once you receive them, what you will do is you will recombine the 2 matrices, obtain R, obtain A, and compute the inverse A prime. Then once you get inverse A prime, you can compute the original plain text by multiplying back to the transform text that you got earlier. Okay? And this will result in the original plain text. So what does information slicing give to you? Okay? And at this juncture, you should be asking, isn't this the same as encryption, right? And the answer is no, it's not the same as encryption. All right. Why is it different from encryption? Now, in encryption, what actually happens is that you have an encryption function that takes a plain text and transforms it into ciphertext. Now, if you have the right key, you could invert this and you will get the plain text again. Now, information slicing is slightly different because when you slice out information and send it down individual paths, recovering some of these fragments will not give you any more information about the plain text itself. Right? If you don't have the minimum threshold fragments, then you just don't have enough data to reconstruct the original plain text. Right? And so in this way, it's different from encryption. Furthermore, yes, it has some similarities with network codings. Secret sharing. Okay. So I'm about to get to the good parts of this very soon. Right? So the nice thing about this approach is that the threshold is settable, meaning that you can set the threshold to 4 paths. For example, if I pick 4 paths and I have a threshold of 3, I can change this in the middle of a session. It's very easy to do, right? And more importantly, you do not need any kind of public key infrastructure to share the keys. Right? This, unlike say, if you have a public-private key pair and you're trying to transmit data, then you have the meta problem of trying to exchange the public and private key pairs. Right? So you don't need a PKI for information slicing. And the same technique can be adapted to provide anonymity as well. So what about anonymity, right? You take a quote from the paper. It says that anonymity can be built out of confidentiality. And the essential idea is we're going to hide our point-to-point communications by engaging a large group of forwarding peers. Right? I'm not just going to talk to my endpoint directly. I'm going to engage a whole lot of other peers as well, the forwarding nodes. And these forwarding nodes will add a little bit of confusion into like who's actually talking with you. Right? And that's the essential idea. So in this technique, you let each of these forwarding peer know its next hop, and they know their parent hop. So individual hops use information slicing to forward data on confidentially. Right? And to further confuse analysts on operating on the network, the destination hop may still forward data. So if you're trying to do this on a traffic analysis kind of, if you're trying to employ a traffic analysis kind of attack, then you find that looking for where the data actually ends, where the forwarding actually ends, may not reveal any information about who the real recipient is. So this is conceptually like showing mixes, where there's a shuffle step, and then you forward it out to more nodes. Okay. So this is the diagram that I obtained from the paper that describes how you would actually perform the anonymity kind of transformation. So, for example, if I was Alice and I wanted to talk to Bob, what I could do is I would use confidential means to send some slices of data to both B and W. Right? And if you notice from B and W, they will not actually have enough information to recover the actual plain text itself. Right? Each of the B and W will only obtain a slice of the information required to reconstruct the final plain text. And it's only upon forwarding to Bob that all of these slices are realized and you can actually recompute the plain text. This is how anonymity actually works. Notice that Bob also continues to send on to X and Y. This is to further confuse traffic analysis kind of things. Very briefly, we have some results from our anonymity and confidentiality work. And essentially, so the results don't really indicate much. I mean, the point of this evaluation was not really, you can't really measure how secure things are. However, we can at least provide a benchmark on how well they perform in reality. And you can see from over here, the takeaway from this graph is that if you have more paths, then the bandwidth drops because you need to perform more notice computations.
So going back on the side, so typically really quite strong and then property. I mean, when you formalize
What was that word?
sorry, that was, I think this is really strong. This is stronger than the
Yes, this is not unlimited.
Well, it goes encrypt, right? So they're encrypted.
Over here, we don't use encrypting, we use the confidentiality mechanism.
It's just slicing the data and sending it. If you have the slices.
Yes.
And I guess
Exactly. Exactly. So I did not produce this paper, first of all. We borrowed the technique from an existing paper. The existing paper talked about anonymity kind of analysis. So they had a metric for computing anonymity, and it involved something like if you're an attacker and you get this amount of control over the network and a certain number of slices and the type of data fragments, then your anonymity starts to drop in a curve. It's sort of like how to describe it. There's a bend, there's a knee in the curve that drops precipitously after a certain number of fragments.
so
that's
that's
how
not
the
that, you're just measuring the overhead.
Exactly. We're just borrowing the technique and demonstrating that it can work to provide these properties.
But the overhead's pretty high, right?
The overhead is pretty high,
I
exactly.
mean, the interest in this would presumably be that as networks get faster and faster, the speed of encryption is not getting faster because it's data touching. Whereas this conceivably could run at network speeds, but it's running very slowly.
It is. So the main reason why it's running very slowly is a couple of reasons. First of all, we did all this simulation in software. The OpenFlow switch was in software, and everything was running single threaded. Now, I believe if we made this run on an NPU, like actual FPGA kind of implementation. You could greatly parallelize this thing
I
and make it a lot more straightforward.
I lost track of
Sorry,
where the reality that you run dates ended, and figuring out a good idea of the diagram. Okay, whose idea was it? Where did this paper come
MIT. So, in summary, why would you actually pick our code, right? First of all, there's no more guesswork of the topology. Right? We're absolutely sure about what the network delivers to you, and therefore we can give to you guarantees when we make the pass. Second of all, it's backward compatible, meaning that you can use your existing network devices on our IronStack system. It's incrementally deployable, meaning that you don't have to transition your entire network over to OpenFlow switches right away on the first day. Okay? You can do this as network switches fail, and gradually replace them with OpenFlow controllers and IronStack software, and eventually you can build a network to be a continuous segment of IronStack control network elements. It's easy to scale because anytime you run out of capacity, you just add an NPU. It's all parallel operations, so there's no dependence between among the NPUs. It's customizable for your exact needs. So, for example, if you're running like Netflix and one maximum bandwidth can be done. If you want maximum reliability because you're a doctor and you're operating remotely, can also be done. Right? And our system is resistant to churn. So we have already built the system to pre-provision for failures, such that when failures occur, you don't even notice them at all. Right? This is one of the great selling points for our system. All right, so I'm done with the first part of my talk that describes our existing work. Now, I've addressed some of the serious operational concerns in networks, and in the remaining 10 minutes or so, I would like to talk about my proposed line of research inquiry. So the best network solution in the world, as I described, provides performance, provides reliability, provides confidentiality, provides anonymity, is nothing if nobody knows how to use it or if it's too difficult to learn. Okay? Now, as a step in the right direction, we've already made things as easy as possible. Right? We made it such that as long as you have a network device that works today, you can use it in our system. Right? But I think further measures are actually needed. Now, first let's address one point that says it's hard for networks today are hard for regular users to understand. Right? And many users of a network are not completely literate with data networking. For a lot of people, data networking is just unintuitive, right? Like regular users don't want to know things like, what is an IP address, what's a gateway, what's a network address translator, like DHCP or stuff like that. They just want it to work. Right? I plug it in and I just want it to work. They want it to be frustration-free. Now, as a side anecdote, right, I'll give you a story from this fiber company that I consult for. They built a fiber optic network in Africa, right? So they had a customer who bought a home router, and they plugged the Ethernet cable given to them by the service provider into the wrong port. They plugged it into the LAN port instead of the WAN port, right? The one that connects it up to, that provides the internet up in the home router. So what do you think will happen when this? So what actually happened, right? So first of all, there was a design flaw in the existing network. There was no L2 isolation between any of the subscribers, meaning that if a subscriber sent a broadcast message, everyone else in the network would receive it. And what happened was that other subscribers who plugged in their machines after the errant home router actually got plugged in, ended up in a situation where there was a race condition and a DHCP lease was being offered by the errant home router, right? So subscribers get confused, the devices sometimes accepted the wrong DHCP server, and as a result, these systems had no internet access at all. Okay? And this is like a very benign kind of thing to happen, right? It's purely user error, right? But it could have been much worse. If I know something like that, I could have executed a man in the middle. Right? So the takeaway is that users may make unintentional mistakes. Now, as well, networks are also difficult for administrators to set up and maintain, right? So please be kind to our ITSG staff. There are lots and lots of variables involved in configuration, right? It's complicated and it's more than just the topology. Therefore, configuration is very error-prone, especially if the process is manual. And so here's a story that I got from ITSG, right? A couple of years ago, we had a practice cluster that was located at Upson Hall that had a latent network loop area. Okay? Now, more importantly, that part of the network ran without a spanning tree, so no protection offered by nothing to protect against loops, right? And then something actually happened one day, and I regrettably cannot really disclose what this is, but the problem triggered the loop, and as a result of this, data was circulating at high rates between the router, the practice cluster, and the rows hall router. And this brought down internet access for half of engineering, for all of engineering. Okay? So, what does this actually tell you? What is the lesson we learned from here, right? So, you know, after experiencing these kinds of things, you get the sense that like, networks are very, very rickety. They can break at any moment. And then, you know, if something's working, you really don't want to break it with some careless touching, right? Careless modifications. So all of these hint that something is missing in this technology. There should be something to actually counter-check your operations, to counter-check your configurations on the network. All right, so if I were to summarize what I've learned in these practical deployments, is these 3 points about usability. Network configuration is hard. Okay, it's very, very prone to errors. Users sometimes do the wrong things, and you need to protect them from that. And the problems are not always going to be obvious. So just because you can get your network running today doesn't mean that it'll be running tomorrow. Okay? So how can these problems be solved? Right? You know, I propose 2 different techniques. Right? There are 2 techniques. One would be technological. Right? You could improve, for example, the cohesion between the devices operating on the network. Right? You should know who their peers are, who are they talking to, and you provide better checking algorithms so that these devices don't end up getting the configuration that conflicts with one another. Right? So if you could design devices that intelligently and safely collaborate with software-defined network controllers, you could actually improve the stability side, the usability side of things. Next, on the human side of things, you can lower the technical bar required to operate networks and devices. Right? So, for example, wouldn't it be nice if you had a home router, right? And a home router like this would tell you exactly what you should be doing. Plug cable A into this port, don't plug it into this port. Okay? And it should also tell you, it could also tell you things like when something breaks, how would you actually fix it? Okay? The steps are written down on the home router and they educate you instead of it being some kind of a black box, some kind of a, you know, like to think of networking as a black art. We don't want it to be that way. Okay? So one way we could do this is by designing visual interfaces to express instructions of problems and provide adequate checking to safeguard the user from himself. Okay? So here's an example of a prototype that I built as a patent-pending design. And you know, for example, if you're operating a switch, the switch should be something that would be able to tell you when something goes wrong. Okay? For example, over here, you know, there's a port that is disconnected, and because of that, the impact on the network is that there are no more path redundancy. Right? So this tells you what the problem is and how it could actually impact you. And then it tells you how you should actually fix the problem. All right? So get a network cable connected from one port to any available port on a different switch. Right? And therefore, what we've done is we've made this whole networking thing extremely accessible to anyone, even if they don't have any kind of technical training. This should be the way that things are done. Therefore, now that we have the right tools to improve data networking, it would be nice to have some other tools that aid us in the visualization of the network. And therefore, what I would like to propose for my future work is the construction of a mission control style visualization software that allows you to intelligently control every element in the network, something that also conforms to existing security policy. It should make it convenient for you. It should identify problems before they occur. It should try to fix them for you when they occur. And lastly, you should always check for configuration mistakes before they actually happen. And in so doing, you make it dead simple to use and difficult to make mistakes. So here's a mock-up of how something like that would look like. You might have a system that tells you where the hotspots in the network are. They not only tell you that there are hotspots, they tell you which ports are the hotspots and where the location of the switches are. Okay? And they will also give you a summary of other things that go wrong. It will try to fix problems for you. And in fact, this will just be a mission control, a go-to screen for all your needs in controlling and configuring the network.
The crack problem gets us to get worse.
Alright, so here's a list of the related work that I produced in preparing my paper on this talk. I have some demos available for you. This system is wired up to the OpenFlow network segment that is controlled by IronStack. Feel free to use it. Unfortunately, I could not get the home router to work because for some reason there was no link activity when I connected it to the LAN port. I tried different LAN cables and so on. Maybe the router is broken. But feel free to help yourself. This operates on IronStack right now, and I have some other network device prototypes. I have a switch over here that I talked about with the touch panel control and the intuitive, like tells you what goes wrong and how to fix things, kind of interface. All right. And with that, I am happy to take questions.
So this is a good time for the audience to ask questions, especially because the committee's going to linger. So there's a tendency for the people on the committee to sort of sit on their questions. So, you guys have questions? All right, then we're going to ask the rest of the audience to step out.
Thank you for coming. Especially, oh, by the way, Dave, you should see this. I was going to say thank you to you. That's nice. Yes.
Okay. Yeah, really.
All right, so I think for the session that has joined
Although
us
actually
remotely,
we know perfectly
we
well
wouldn't
who
have to
DDoS
determine
is
this. Okay. So our live session is going to terminate right now. Thank you for joining. And so don't text me right away because I'm going to be in the midst of another round of interviews. But I'll talk to you guys later. Thanks.